Okay, so we're looking next at the application of z-scores, okay, and that's really going to come into probability. So I suppose this is where we get that kind of overlap, I suppose, which is kind of never really gone between your stats and your probability there. And there is quite a bit of potential overlap between the two topics there. They are quite related. Inherently there, I suppose, and in some cases this would even fall more maybe under probability than it would in statistics. So we can use z-scores basically to work about the probability of normally distributed data, of achieving certain data points, but more specifically it's about achieving maybe a value greater or less than a particular other value that we have in our data set. So we use this really to compare or to determine whether a certain value maybe is an extreme value, and we might use it to look at whether it's possible to get a more extreme value, whether that's very unlikely or is in fact likely, and it just allows us to compare, to interpret the data in a more specific way. So when we're using our z-scores, it's really important to make sure that you're remembering that the formula and tables book is going to give us the probability that a certain z value is less than or equal to a particular z-score. Okay, to a particular value that we have. And you can see the diagram that they have on the left there, which is the same one that's included in the formula and tables book. So it will give us the area to the left-hand side of this particular z-score value, remembering that a z-score, by definition, is a number of standard deviations. Okay, so we're working in that standard normal distribution, which is the one that has a mean of 0 and a standard deviation of 1, so hence the 0 and 1, 2, 3. And a z-score is a particular specific standard deviation or number of standard deviations within that. And the formula and tables book will give us the probability of me achieving a value less than or equal to that. Okay, and we generally say less than or equal are kind of essentially equatable, or equitable is the word here, as the probability of getting a z-score equal to a specific value is quite small. So the table here, I suppose, that we have on the right as well is just an example of the page that is in your formula and tables book, and we will look at it in more detail when we're looking at some of the examples here later. But you can see that we have the z-scores on the outside here. On the left hand side we have kind of nearly the stem, if you like, of them, so the first decimal place, and then on the top we have a second decimal place. So generally we're going to limit our z-score values to 2 decimal places, which gives us maybe the most accuracy in determining these values. And just allows us to pick out the specific probabilities that we might need. The values all on the inside then are those probabilities, the probability of me achieving a z-score that I've identified from the table there. Okay, just kind of to recap really on what I've said there as well, if we're being asked the probability that a certain z value is less than or equal to 1.65, I am looking for the probability that the result will be less than or equal to 1.65 standard deviations from the mean, which is the area under the curve up as far as 1.65. If I'm being asked maybe for the probability above 1.65, that is this smaller blue area here. Okay, so if this is my 1.65, that's this smaller blue area here, which is the same as 1 minus the probability that z is less than 1.65. So you can kind of see by comparing the two diagrams here, the region that I want to eliminate is the same as the region that I have over here. And from what we said when we introduced the distribution, the total area under the curve is 1, because we're tying it back to that idea of probability. And of course, total probability is always 1. These relationships here in calculating our z-scores can be quite helpful to allow us to become a bit more fluid or fluent in kind of doing these calculations without needing to really, I suppose, sit and think about it all the time. But at the same time, we can work it out through use of diagrams. We can work it out through just kind of being, I suppose, consistent and being quite confident in what we're doing there. But it's no harm to kind of learn some of these values off either, if you would like to do that, if that would help you feel a little bit more settled in what you're doing. So the steps we're going to follow are fairly straightforward. We will calculate whatever the standard score is for the particular data point that we have. We will sketch the relevant areas, so whether we're going to the left or the right, or even in fact in between, and then we will find the relevant probabilities in the z-score tables. So let's look at 3 examples here to get us going. We want to find the probability that z is less than or equal to 1.3. So first example here is in the perfect format to be read directly from the log tables. So we'll go to our formula and tables book here. We're looking for 1.3. So That is 1.30 for all intents and purposes here. So reading that from my log tables, that's going to be this value here, where I have 1.3 and 0 as the second decimal place, and that's an answer of 0.9032. So the probability that a z-score is less than 1.3 or equal to 1.3 is 0.9032. Looking at the next example, the probability that z is less than or equal to minus 1.3. Okay, well, by doing a quick sketch, we should hopefully see that that is going to be the same as the probability of positive 1.3, which is equal to 1 minus the probability that z is less than 1.3. So what I've got here is z greater than 1.3. So therefore 1 minus probability that z is less than 1.3, which is 1 minus 0.9032, which is 0.0968. The last example we have here is the probability that it's between two particular z-score values. So if I was to kind of reduce this down myself, I might do some quick sketching of the areas that I want to consider. I want to consider 1.65 here, everything below 1.65, and I want to then subtract anything to the left of 1.3. Okay, that's what I would like to get rid of. That will give me the blue area that I have identified in the question here. So all of the area to the left of 1.65, and then taking away that small piece of negative area here, which would essentially line up with this part here that I want to remove from. So putting all that together, that's going to be the probability that z is less than 1.65 minus the probability that z is less than minus 1.3. Okay, and some of these we've already identified, some of them we haven't. 1.65, let's have a look at that one here. That's going to be 1.6 is here, and then 5 is here, so that's 0.9505. Probability that z is less than minus 1.3 was our answer from the previous example. And we can combine those together, minus 0.9505, or no, 0.9505 minus 0.0968 is 0.8537. Okay, so you can see there a lot of work to be done. Okay, sketching can definitely help us in just kind of keeping everything consistent and keeping everything clear for ourselves working through it. There's a little bit of, I suppose, extra bits coming up there. We can see use of negative standard deviation values, but when we go to the tables start at 0. Okay, they're not going into the negative standard deviation values, and that's all down to the symmetry of the curve. Because the negative side will match up with the positive side, the tables only include half of the values. So you'll notice even that the probability that I get a mean or a standard deviation of 0, that I get the actual middle value, or a value less, I should say, of course, than the middle value, which would be the average there, is 50%, because we expect 50% of the information to be either side of my standard deviation, or of my mean there, I should say. So I suppose that's one thing to consider. There's 50% of the information on both sides. The other thing then is just that symmetry that I'm pointing out there. So because of the symmetry of the curve, we only need to have values for half of the curve, because it's going to match up with the values on the lower half of the curve. But just something to note there, if we are kind of concerned about why some of the values that we're using or that we're looking for are not appearing in the tables there for us. So we'll continue onwards, looking at standardizing some real values here and using them in comparison. Again, the heights of students in a class are normally distributed with a mean height of mu 165 and standard deviation of 10. John is 180. Find the probability that someone is taller than John. So I want to find the probability that someone, so we'll call them X, that's picked from this class is taller than 180. Okay, I don't have any way of computing that probability, but since I know it's normally distributed, I might convert it to a z-score. So I'll use the standardizing formula that we met in the last section, and I'll fill in the value. I'm filling in 180 for my x value, 165 as my mean there, standard deviation of 10, that's going to be 15 over 10, which is 1.5. So I'm being asked for the probability that a z value is greater than 1.5. Okay, from what we've looked at, with our little sketches here. That's this section here, which is equal to 1 minus the probability that it is less than 1.5. So 1 minus, let's go look for 1.5. Okay, it's nice straightforward. 1.5 here, 0.9332. Let's fill that in. 0.9332, and that's going to give me an overall answer here of 0.0668. Okay, which is 6.68%. Okay, so given the fact that John is already 1.5 standard deviations above the mean value or the average value in the class there, it's probably not surprising that the probability of someone being taller than him is quite small, 6% or even 7% there if we round it to the nearest percentage. The second part, 8 people are chosen at random, find the probability that at most 2 are taller than John. That's an example of a Bernoulli trial. Okay, where the probability P of success, okay, is the probability that they are taller than him, which is 0.0668, and the probability Q of failure is the probability is the opposite of that they are not taller than him, that they are in fact smaller than him, which is the alternative, the 0.9332. Okay, we want at most 2, so the probability of getting at most 2 means getting the probability of none plus the probability of 1 plus the probability of 2. So we want, out of the 8 people chosen, that none of them are taller than him. So the probability of success is 0, failure is 8. We also want then that out of 8 people chosen, 1 person is taller than him. And then we want, out of 8 people chosen, 2 people are taller than him. Okay, in some cases this a calculation of at most might be quicker to do by doing kind of a 1 minus here, but in this case it definitely is just quicker to look at the 3 particular cases that we want there. The reason we have to use a Bernoulli trial is that we're not that, I suppose, bothered where in the 8 people these two people occur. Okay, so solving all of that out gives me an answer of 0.987066, which is about 98.7%. Okay, and again, given that the probability someone is taller than him is around about 7%, it's quite fair to suggest that then the likelihood of someone being taller than him is quite small. Okay, it's quite small, and at most 2 people seems quite reasonable, really, for us to kind of come across there. So we'll look at some of the exam questions here. As I say, we mightn't do maybe every single exam question, but we'll do a few of them, surely. So starting off here, an online word game involves trying to guess a 5-letter word in as few attempts as possible. Okay, so reference to an unidentified word game. And for this game, each player is given a score S, and based on how many attempts it takes them to guess the word. And Ireland players' scores are approximately normally distributed, mean of 3.87, standard deviation of 0.36. A player is selected at random. Find the probability this player has a score of less than 3.5. So we want the probability that if I pick a person, that their score is less than 3.5. So we need to convert that to a Z score. So looking at my Z values here, I need my mean, which is 3.87. I need my standard deviation, which is 0.36. And my X value I'm using is 3.5 here. Okay, so immediately I'm looking here and I'm like, right, that is below average. Okay, that is below that average value for the country here. So just bearing that in mind, I'm expecting a negative value here. So I'm going to have to adjust that in my calculation of the Z score value. It's minus 1.02778, which if we round upwards to use our Z scores, minus 1.03 is probably the best for us to go for there. So we're being asked for the probability that Z is less than minus 1.03, which corresponds with this section here. Okay, that's going to be equal to the probability that Z is greater than the positive 1.03, which is up here, which corresponds with 1 minus the probability that is less then 1.03, which is 1 minus, let's go look for 1.03 in the log tables here. So 1.03, sorry, it's down here, is 0.8485. So let's fill that value in. 1 minus 0.8485, and that is 0.1515. Okay, which is about 15.15% there. Okay. Continuing onwards, let's look at another one. In an athletics, can't talk anymore. In an athletics competition, there were a number of heats on the 1,500 meter race. In the heats, the times that it took the runners to complete the 1,500 meters were approximately normally distributed, with a mean time of 225 seconds and standard deviation of 12. Okay, so again, I see reference to normally distributed. I'm like, right, Z scores is probably going to be useful here. Okay, so it's a particular race. Find the percentage of runners in these heats who took more than 240 seconds. So it seems to be here what's normally distributed is the times. So we're looking for the probability that this is greater than 240. Again, going to be largely following the same technique or the same steps that we've been doing all along here. So I'm just filling in the values kind of quickly here so that we can continue flying through it, because I think there is a nice part coming up in the second part here. So 1.25, we want the probability that you're greater than 1.25, which is 1 minus the probability that you're less than 1.25. Okay, and all of that really, again, just coming from my curve here. So I want this black section up the top, which is 1 minus all the section that I have in white there. Okay, looking at 1.25, that is 0.8944. 1 minus 0.8944, and filling that in gives me an answer of 0.1056. Okay, as a percentage, 10.56% there of runners took more than that time. Okay, so a reasonable number percentage as well to get for that, with an average of 225, probably a reasonable number there. We're over 12 seconds over the average there. The 20% of runners with the fastest times qualified for the final. Okay, this one I feel like was a bit of a trick, so we're going to highlight that straight away because that's a potential trick one there. Assuming the race times were normally distributed as above, work out the time needed to qualify for the final. Okay, so there is a little bit of a trick in this one, because if we're thinking of a race, it's the times that are normally distributed. Okay, so it's the times that we're working with here. Okay, fastest time is going to also be the lowest time. Okay, if you're fast, you're on the lower end of the information here, of the distribution. So we're looking for the 20% that are down here. We essentially want to say that we want a particular Z value here so that 20% of the information is less than it. So we want the probability that Z is that you get less than that, less than or equal to that, being 20% or 0.2. Okay. So I suppose the corresponding value really for that is going to be the probability that you are greater than that, being 0.8. Okay, so I suppose that's the opposite situation here, is the probability that you're greater than that, being 0.8. Okay, and we can consider this minus Z if we want to. Okay, sometimes it can be quite a kind of convenient or easier nearly just to acknowledge that as a negative number here straight away. So we want the probability of being less than that, being 0.2, so the probability that we're greater than being 0.8. Okay. So let's kind of look at how all of this would come together here. So I want a probability of 0.8. So let's look at a value that will give me that sort of probability. Okay, and looking at my answers here, the closest I can get to a probability of 80%, looking at my Z-score values, is probably going to be 0.85 here. Okay, even between maybe 0.85 and 0.84. Okay, we could kind of go with really either of those ones there would be acceptable there. So either the 0.85 or the 0.84 are definitely going to include 80% of the information there. We'll go with the 0.85 because it is over that 80%, but you could equally go with both, or indeed take an average of the two there and go with your 0.845, for example. But that's the idea that we're working with here. Okay, so based off that, we are essentially saying that the z-score value needs to be 0.85. Okay, so, and in this case, we already know that for whatever my x value is in this case, my z-score value is going to be negative. Okay, so an answer of minus 0.85. So recapping over that again, we want a certain z-score value for which the probability of being less than that value is 0.2. That's going to line up with the probability of being greater than that value being 0.8. Okay, and we already should maybe hopefully remember from a bit of kind of fluency with those ideas there. Where I'm kind of getting that idea, I suppose, is the probability that z is less than minus z is 1 minus the probability that z is less than positive z. Okay, so that's why we're kind of nearly getting that 0.8 is the probability that z is less than positive z there. Okay, making that connection there. And that just allows us maybe to look at our log table specifically and look for that specific probability of 80% there, which works out as a value of about 0.85. We know it has to be negative because we're expecting it to be in that lower portion of the information there. So I suppose solving out now is all that's left to be done. So 0.85 times 12 is 10.2, and x is 225 minus 10.2, which is 214.8. Okay, so the time needed to qualify for the final is 214.8 seconds there in this particular example. Okay, so we look at some of the other examples here. Okay, there's I suppose a lot of different ones coming up in across these questions here, but we'll fly through some more of them because I think there is a lot of good examples in this. A company produces calculator batteries. The diameter of the batteries is supposed to be 20 millimeters. The tolerance is 0.25 millimeters. Any batteries outside this tolerance are rejected. You may assume that this is the only reason for rejecting. The company has a machine that produces batteries with diameters that are normally distributed with a mean of 20 and a standard deviation of 0.1. Out of every 10,000 batteries produced by this machine, how many on average are rejected? Okay, so that's all going to come down to, I suppose, really the probabilities here. Okay, the probabilities of getting batteries with diameters within this particular range. So mean 20 millimeters, standard deviation 0.25. Any batteries outside of this tolerance are rejected. Okay, so let's have a look. So that's my tolerance here, excuse me. My standard deviation is given down here as 0.1. Okay, if they're outside of this range, we want them to be rejected, so we're allowing them to be within 20.25 and 19.75. Okay, that's essentially the range that we're looking at. So the diameter is supposed to be 20 millimeters. Okay, that's, I suppose, what's been identified as the desired diameter of the batteries here, but we are allowing between 19.75 and 20.25 in terms of our batteries. Okay, we're allowing either of those or within that range there, but it's not allowed to be outside of that range. So in terms of my z-score diagram here, that's going to be, I suppose, essentially, depending on where the z-scores are going to land here, we're going to be looking at a portion between two particular values. So we'll lay out our z-scores here. We'll work out both of them. So 19.75 minus 20 over standard deviation 0.1. That's given me an answer of minus 2.5. So I can mark that one in. And on the other side, 20.25 minus 20 over 0.1 is 2.5. So really we're being asked between 2.5 and 0.25 here. Okay, so that's kind of the range that we're allowing ourselves to look at. It's between really the same particular value here. Okay, so we're looking between the same value really. So that kind of does make our calculation a little bit easier for us in this case. So we really want the probability that z is less than 2.5 minus the probability that z is less than minus 2.5. Okay, bearing in mind that we already know that the probability that z is less than minus 2.5 is 1 minus the probability that is less than the positive 2.5 there. Okay, but we'll work out the values individually. Let's just go and double check for 2.5 what our z-score value is, and it's 0.9938. So 0.9938 minus 1 minus 0.9938, and let's just work out that expression there. 0.9876. Okay, that's my overall answer here. 0.9876. Okay, so I only want values, I suppose, that are within that range. Okay, so I only want values that are within that range. Okay, on average then, I would expect that 9,876 are, I suppose, accepted here. So therefore, that's going to mean that 10,000 minus 9,876, 124 are rejected. Okay, I suppose there are multiple ways we can look at that. We've maybe gone a bit backwards by looking for the region on the inside here, but kind of just working with what we had calculated. But really, we might be looking at kind of the outskirts of that instead. And again, that would be equally acceptable there in terms of working our probabilities. So part B then, setting on the machine slips so that the mean diameter of the batteries increases to 20.05 while the standard deviation remains unchanged. Find the percentage increase in the rejection rate for the batteries from this machine. Okay, so let's have a little look. So the mean diameter has increased based on what it previously was, but we're going to treat everything else as the same. So 20.25 minus 20.05 all over 0.1 is going to give me an answer of 20.25 minus 20.05 over 0.1 of 2. And on the other side, it was 19.75 minus 20.05 all over 0.1, which is sorry, I forgot to put in the minus there, which would be quite important on the decimal point, minus 3. Okay, so slightly changes the region that we're looking for. Okay, slightly changes the region that we're looking for. So let's just look at the specific cases in this time, because we're focusing, I suppose, really on rejection here. So 2 is here. I'm rejecting if it's in this region here. So the probability that z is greater than 2, which is 1 minus the probability that z is less than 2, which is 1 minus, let's look for 2 here. So 2 is 0.9772. Okay, and that's going to give me 0.0228. Okay, 0.0228. We also have to consider the other region, which is minus 3, which is the region to the left here. So the probability that it is less than minus 3 is the same as 1 minus the probability that it is less than positive 3. Okay, that's using one of our kind of quick little rules from earlier. We'll look for the probability that it is less than 3 also, which is 0.9987. So 1 minus 0.9987 gives me an answer of 0.0013. Okay, we can add the two together. Okay, to work out the total probability. which is 0.0241. 0.0241 as my overall rejection rate now. Okay, my overall rejection rate here. In terms of how many that would be, we'll times that by our 10,000 here. It's 241. So that is an increase of, I suppose, a rejection of 241 over our initial rejection of 124, which is an increase of 194. Okay, so that's 194%, which is a 94% increase, of course. Okay, a 94% increase. Okay, so a 94% increase to be seen there in our calculations. Okay, really for percentage increase, I mean, the way that I've calculated there is perhaps a little confusing, so let's just make it a bit simpler. Really, I suppose we would look at what the increase is itself, which is 117, and use that increase over the actual value and multiply by 100 to get our 94 there. Okay, a bit more straightforward. I'm not sure why I kind of went a bit roundabout at it there, looking at kind of the overall 100% idea of it first. Okay, we've some more exam questions here. Again, it's a lot of the same. Okay, it is a lot of the same. If you look at the first year Static Common Maths exam, distributed mean mark to get to the county stage, a particular specific result within 10% of students, a merit, a certificate if you get between certain results, so the same idea that we've looked at. The data on speeds, okay, proportion of stretch on the road travelling over 95, so again, working that probability, 70% of speeds were higher than his speed, find the speed at which he was driving, give your answer correct to the nearest whole number. Okay, so again, the same idea coming in there. Looking, I suppose, at this particular example here as well, the diagram shows the standard normal curve. The shaded area represents 67%. Find the value of Z1. Well, that's just a matter of looking at our Z-score tables, looking for 67, which I can see in here straight away. So that's 0.44. So that is a Z-score value of 0.44. Okay, 0.44 standard deviations above the mean. And again, I suppose even looking at that, that really means there's about 17% of information in that section there, because we know there's about 50% of the information below that. Okay, last one then again, same idea, looking at our Z-scores with reference to the income made by particular people, okay, and it's normally distributed. So you can see there are a lot of the same things coming across. The key things really are going to be working with those Z-score values, working with your little sketches, and being able to use the Z-score tables there in doing those calculations.